Hello and welcome back to our OpenGL Math Visualizer stream, or series rather. Today we're going to be continuing on with some more surface or just rendering in general, and we're going to be using the geometry shader like we did last time. But today we're going to be rendering more generalized 3D surfaces. So we'll look at exactly what that means. And we'll go through some math and then we will write some code. First, wanted to go through some fixes from last time. So number one, sorry, let me just pull up the controller. All right, so number one was in the main file the reason why we weren't seeing any arrows was simply because in update camera matrices, we never called we didn't have this for loop to update the camera matrices in each of the programs. So what ended up happening was the arrow never received the projection or view matrix, so it just kept getting zeros and zeros, and therefore it wasn't projecting anything. And then another thing that was more minor, but it's important nonetheless, was that we had a little bit of an extra line here with the matrix calculation. So I'm going to go back to the arrows here. And what we ended up calculating with, I believe it was this calculation up here, where we had two basis vectors. What we ended up getting was these weren't perfectly orthogonal. So in essence, what we did was we took the x unit vector, so I'll call it I hat, and then k hat, the z unit vector, and then we transformed these into a different, into a rotated plane. So we essentially rotated the xz plane, and I'm going to call it, let's say, I hat prime and k hat prime, and this still worked. They were linearly independent, which was great. They were linearly independent, which meant they spanned a plane. However, they weren't orthogonal or perpendicular. What I mean by that is there was some parallel component there to these vectors. So I hat prime dotted with k hat prime was not 0. So therefore, we were getting a bit of a distortion. It's a bit like a shear transformation. Like a good example would just be like, so we have our orthogonal vectors, and then we kind of do it like that. So we kind of made a coordinate system that was made up of parallelograms instead of squares. So our circle ended up looking like an oval, and we didn't get to see that. But a good trick of just making sure that they're orthogonal so that the circle remains a circle instead of an oval is that we can just do something called a reorthogonalization. And that's this line here. So I'm just going to copy this into OneNote and just go over this. All right, so we essentially had our two basis vectors u and v, and they were not orthogonal. A good way to make them orthogonal is just to take this dot product, so is just say u dotted with v, and this is a scalar value, so this is some constant k, and multiply this times the vector u. So essentially this component right here is the vector component of v parallel to u. So it's the parallel component of v to u. And since we want them to be orthogonal, we can just simply subtract this vector component. So essentially, if this was v and this was u, we'd have that this vector right here is u times v dotted with u. We just get the magnitude from the dot product, but then we just multiply it by u, and then if we subtract this, we get a perfectly a perpendicular value. So this is v minus that whole thing. So the expression is v minus u times u dotted with v. and that will be normalized and when we in the calculation there. So that was just one quick fix, and I guess I'll show you guys the actual arrow now that we got to see it. But yeah, so this is our arrow. There's 3 of them. The blue is X, red is Z, and green is Y. I believe that's how it works. Or it might be the other way, or I forget which is X and which is Z. I'm gonna have to find it. X is red, so my mistake. So X is red, Z is blue, and Y is green. So yeah, that is the first part of this, and now we're going to be moving into surfaces. So I'm just gonna type in the comments here. Oh, that's not. There we go. All right. So I didn't want to do that, but someone asked me to start doing timestamps, so I'm just going to put that in the comments, and then I'll transfer that from the comments to the description after the video, because that has timestamps on it, which is cool. Okay, so 3D surfaces. We kind of looked at this a little bit when we did normal mapping, and we have also looked at this with the sphere a little bit, where we just represented a general, just a very specific 3D surface that represented some sort of relationship. So the sphere here we had was the set of 3D points, so the points in the 3D space that that satisfy this relationship, and that's a very specific relationship. And you can also have an oval that would be something like, or not, an ellipsoid, sorry. You have like x squared over 9 plus y squared over 4 plus z squared over 16 is equal to 1. And that's a bit of an ellipsoid, where the axes are scaled differently. But there's also a more general type of surface that you can do, and it becomes much more valuable, and that is when you define it, just the height of the function. So for example, we have the height z, it's usually z, is equal to x squared plus y squared. So let's go and look at what this looks like in GeoGebra 3D. So if we just type in x squared plus y squared, we get this little cone, or not a cone, but a paraboloid, where the blue is z. So it's the height, essentially. And you can see that it kind of increases in both directions. And this is just the Cartesian distance from the origin in the xy plane of the point. But that's just the height. In OpenGL, instead of y being the quote-unquote, or instead of z being the quote-unquote height, we represent y as the height. So we could do this in OpenGL using y is equal to x squared plus z squared, and it'd be the same thing. But if we consider this as a function, so let's call this f is equal to x squared plus z squared. This is just f of x and z, which looks an awful lot like what we did with the sphere, right? Where we essentially had, where was it? I forget where it was. This was the circle. It was right here. So with the sphere, we had 2 parameters mapping to a 3D point. So if we wanted to represent the sphere as a vector function, this would be a function of theta and phi, keeping the radius constant. And this is just going to be, what did we say? X is cosine phi, cosine theta. Y is sine of phi. And z is cosine phi, sine theta. So this is just a vector function that you can use to map these 2D parameters. And this is the same thing. Except now we're getting a scalar, but we can use this to map to a point because this is just the height. So this is y. So therefore, we can represent r, any point on our surface, as a function of x and z, as just the points x, and the y coordinate x is the y coordinate is something, and the z coordinate is z, but the y coordinate is just this function here. So f of x and y, or x and z. Sorry. So we specify a surface function, and that gives us our parameterization. It just calculates that third component there. So in our case here, we would have the function is x, then the y coordinate is x squared plus, I keep writing y, x squared plus z squared and z. And that's just two parameters. With the sphere, the one difference here is that we had a very confined domain that we could define our function on, but if you look at this, this is defined for every single point in the xz plane. And I suppose for a sphere, you could say the same thing. These points are defined for every point in the, this function is well defined for every point in the phi or theta phi plane. However, there are repetitions. That's why it's a sphere. You could do theta goes from 0 to 18 pi, and phi goes from minus 10 pi to 10 pi, and you would still just get a singular sphere because it wraps around with this stuff, because these are all periodic functions, and it's just a composition of periodic functions. With this, however, it's not very periodic, because we're spanning the whole xz plane. The function x never repeats. If you give a different value of x, the output x will be different. That's just, I mean, I don't know how else to explain it, but this is a non-repetitive function. So we're going to have to consider how to actually represent this, because with the sphere, we procedurally generated the vertices and then stored those in the vertex buffer object. However, with this, that might be a little, it might be a little inefficient to do that. So what we're going to do instead is actually just do this calculation for f in the geometry shader. And the difference is we're not going to be able to render one quote unquote vertex per instance. So with the arrows, what we saw was we were drawing, where is it here? Every point represented an instance, and that's just not going to be the same for this, because we have just so many more points, and we're not generating everything solely from the geometry shader. And another limitation, or another difference, is that with the arrow, we had a well-defined, that file doesn't exist. We had a well-defined number of points. We knew exactly how many vertices we were going to be generating. But with the surface, we might want to be a little more flexible about it. Like we might want to allow a finer surface. So that max vertices might be 100, could also be 1,000,000. But the geometry shader is not going to output 1,000,000 vertices. It just can't do that. So what we're going to do is we're going to go back to rendering every point as a point in the vertex shader and pass one point through the vertex shader to the fragment shader. But we're not going to store these points because we can just calculate them easily in the geometry shader. There's no point, because there's little computation that's or little time that's lost during the computation, just because the geometry shader is so fast. But if we were to store all those points, that'd be a massive waste of space on the computer. So yeah, we're gonna essentially calculate everything in the geometry shader. And we'll also look at how to pass in the points. We won't be storing points. We will actually not be storing any vertex data. we will only be storing instance data. So it's kind of a combination of the arrow with the sphere, where we're rendering instances as a vertex, but we're also drawing each vertex since we want to vary the amount of vertices that the geometry shader outputs. So let's first go into some math. So we did the arrows, and now we're going to look at the mathematical introduction of, or more math in the surface. So this is our, and we could, I guess we could just go ahead and start writing code now. But I don't want to go back and forth between OneNote and the code. So what we're going to do is we're going to look at normal vector calculations. So we saw that in the geometry shader for the arrow, we had to output a normal vector, and it was well defined, and you could easily calculate it with each point just because it was a circle, and then you had to rotate it some value. We're going to kind of do something similar, but the normal vector will vary from surface to surface, and I'm going to talk about how you actually define a normal vector right now. So adhering to the proper cyclical coordinate system, where you have x cross, or sorry, we'll use unit vectors, I hat cross j hat is equal to k hat, and then j hat cross k hat is equal to I hat, and then k hat cross I hat is equal to j hat. So we're using this, and we'll see why this is important. But let's just examine a general surface. Let's say x squared plus z squared is equal to y. So we'll have, I'm just going to say this is our xz plane. So I'm going to do z here, x goes out this way, and then y comes up like that. And again, this has to be this way because of the right hand rule and this little cyclical stuff. Just if you do the cross product of x and y, then you get z if it's in this configuration here. So we have a point in the xz plane, that's called xz, and we calculate that, and it gives us some value. Let's say x f00z. So this is where f00 is just the function, the value. So we'll say the surface kind of does something like that, and forgive me for screwing this up, but the surface will change with x and z, and you're not supposed to get anything out of that drawing. But essentially we're just mapping every point in the plane to a height. That's kind of what I was getting at there. But just for the normal calculation, if you watch the normal mapping video, a general way to calculate a normal vector for any surface is just to take the difference in one direction, take the difference in the other direction along the surface, and then take the cross product. Just like that. So for us, we're going to have an xz point here. So this is xz, and we'll say that this is x and z plus delta z, and this point up here is x plus delta x z. So this is in the direction of I hat, and this is in the direction of k hat. So we want our normal vector pointing out of the paper or out of the screen, so that's why we do I hat cross k hat, and that gets us j hat here. Or, sorry, no, other way around. K hat cross I hat is j hat. So j hat is equal to k hat cross I hat, as we stated up here. But to get a normal vector for any surface, once we start incorporating that third point, let me actually check how loud the music is. All right, it seems okay. Okay. So in order to actually incorporate that third point, let's just look at this first point. So we have I'll just say that's our surface. So this is going to be x f00 z, and then this is going to be x f01 z plus delta z, and then this one is going to be x plus delta x f10 z plus, or just z there. So to get this normal vector, we can just simply take the cross product between these two vectors here. So what it comes out to be is this vector is just going to be, it doesn't increase in the x direction, so I'm just going to take this coordinate here and subtract the original point, and we have f01 minus f00 and then delta z. And then the same thing over here. We have delta x, f10 minus f00, and no changes in the z direction. So if we take the cross product of these two terms, we will get a normal vector that points out of the surface, which will be what we want for the lighting. A little more generalizing, or a little more of a calculus definition is if you take the limit as delta x and delta z go to 0, I'm not going to get into why this happens, but it's just a little bit of calculus. You're essentially going to approach that you get the first vector, so along the delta z is going to be 0, delta f, delta z, and delta z, or something like that. Scaling doesn't matter too much. And then the other one is going to be delta x, and then delta f, delta, or actually, sorry, this is going to be delta f times delta z, df dz times dz. And then this is that. So you're essentially saying, all right, well, what's the derivative of f with respect to z? And then we just multiply that by the amount that we change in z. This is kind of the linear interpolation term. Or not interpolation, approximation. And if we just factor this out, so we get this is delta z, 0, df, and I'm just going to shorthand df dz with the subscript z there. And this becomes 1 delta x f 0. And if we take the cross product of this, we get a delta z, delta x, multiplied by some value. However, since this is a normal vector and we're going to normalize it, these constants don't matter at all. So we get that our normal vector, the magnitude of the normal vector doesn't matter at all. So we're essentially just going to get the cross product of 0 delta z f1 with 1 delta x, or the partial derivative of f with respect to f0. And that's going to be the normal vector calculation. Sorry, my computer keeps turning off. I just need to turn the go to sleep function off because I want to keep it on. I forgot to do that beforehand. So take that in, digest that for a second, and we'll run through an example. So once again, we have our function, which is f, and in our example, let's say f of x and z is equal to x squared plus z squared. So that's this right here. Actually, no. Wait. Yes, that is correct. Sorry. The height y is equal to x squared plus z squared. And I suppose if you wanted a bit more of a vector definition, I mean, I guess I just gave you a vector definition. But I suppose that we could have just skipped all this and taken the partial derivative. You know what? Let's do the example in a second, but I'll give you the calculus with vectors. So let's consider our point again as r x z is equal to x, f of x, z, and z. So that's our point defined by, that's the surface essentially, defined for all x and z, or whatever x and z f is defined for. And let's take our partials. So partial derivative of x, or partial derivative of r with respect to x, gives us, well, you just differentiate term by term. So derivative of x with respect to x is 1. Derivative of f with respect to x is just the partial derivative of f with respect to f. That's going to be case by case. And then the derivative of z with respect to x is 0, because as x changes, z does not change. X can do whatever it wants. Z is not dependent on it. And then similarly for delta, the partial derivative of r with respect to z, we get 0 partial z of f and 1. So the opposite, and that's exactly what we got up here. And we just kind of negated the constants here, or we got, just ignore the constants. So we'll take this cross product now, in an example. So let's go ahead and consider f of x and z is equal to x squared plus z squared. And let's do our point. So r of x and z, so 2 parameters, is equal to every point here. This is going to be x squared plus z squared, and z. Let's take our partial. So partial of r with respect to z, we'll do that first, is equal to, well, the first term goes away, and then the partial derivative of x squared plus z squared is going to be 2z, and then 1. That's just the middle term came from the partial derivative of f, and then similarly the partial of r with respect to x is 1, 2x, and 0. And then let's take a cross product. So the partials, they give us a cross product, and we'll do a matrix, the determinant here. And again, I will link down below the vector video that I did for the OpenGL video describing why this, or how this cross product works. So you essentially just put the components in the rows with the ijk basis vectors on the top. So it's 0, 2, z1, and then 1, 2x, 0. And then if we expand this out, this has, what is this? So the I hat has a 0 minus 2x minus j hat, and j hat has minus 1, and k hat has minus 2z. So this is equal to minus 2x I hat plus j hat minus 2z k hat. So that is the normal vector right there, defined at any point. And again, this is where the geometry shader is going to come in handy, because we can just calculate it like we're calculating the function at that point. And it will be quite easy to generalize this to any surface, so long as we can write it in GLSL. And we can even use trigonometric functions too. I'll show you an example later on. I'll skip the calculations, but we'll use some cosines and sines and stuff like that, and it'll be super fun. All right, let's start writing code now. Head back into Visual Studio, and we will create a new program. Oh, also, I got the extension for GLSL, so now it looks pretty. It's just about time. I don't know why I haven't, but someone mentioned it to me for the 50th time, and I decided to finally act. And now you can actually see, which is cool. All right, so we'll do surface.hpp. is our class for today. And we'll do some includes. So include glad/glad.h, glfw/glfw3.h. We're going to include glm. We're going to include program because we need to inherit that. And then we're going to include the shader, material, and vertex memory classes. And I think I'm just going to copy that from some other class. I don't want to write that all over again. All right, then we'll do our macros. Oops. So if not defined, surface, HPP. I can't type today. And diff. All right. And then we'll do our class. So class surface, and it's going to inherit from public program. I'm sorry I'm typing so badly. This is the third keyboard I've typed on in today, honestly. So it's just getting used to it. Okay. So we'll start with the VAO, which will be private. So array object VAO. And then we'll have a set of instances. So unsigned integer number of instances, and unsigned integer max number of instances. And that's how we start for now. And then we'll do our public constructor, which will just initialize these for now. So surface unsigned integer max number of instances. So we initialize number of instances to 0 and max number of instances to the value passed in. All right. So what do we need for each service? So we'll have an add instance. So bool add instance right now. So glm, oh, I'm sorry, I already spoiled it. So that's just our boundary check, and then we return true otherwise. But what do we need in each instance? So for now, what we're going to be doing is we're going to define one surface, so one function in the geometry shader, and that will be what we use for all instances of this shader class. I guess you could have different shaders, but for now we're going to keep it as one surface, and we'll expand later on. So to define each surface, we kind of want to give it a domain, because we can't just render from over all real numbers. You just physically cannot do that. I forgot to do the timestamp. I'm sorry. So we need to define essentially a bound. So this will be the bounds on x and z for which we want to render points. So glm vec2 start and glm vec2 end. And then we will also pass in a material. So given that we have our function defined in the geometry shader as something, these are the only two parameters that will differ from surface to surface. And this is kind of reminiscent of the sphere, where we restricted our domain, because we could theoretically do across how many ever things, but with the generalized 3D surface, it actually kind of matters where you define your point, unless it has parametrized points or periodic functions in the definition. But with the sphere, we know exactly how many points we need to define the whole sphere. It's just this little range here, or this little domain. But we're going to define that by passing in per instance. So here we're going to store stuff in our VBO, and we'll do a vector for to have the bounds. So a standard vector of glm. Oops, why did it? glm vec4 bounds, and we will say bounds dot pushback glm vec4 containing start and end, and we'll just pass that in one layout. I need to include vector. Okay. And then we can do our colors. So we'll have standard vector GLM vec3 diffuse and standard vector GLM vec4 specular. So diffuse dot pushback material dot diffuse, and then specular dot pushback, we're going to pass in the specular color of the material plus the shininess value. And then there's one more thing that we do not have right now, and that's going to be the resolution. So with the sphere, I'll go back to it. We had this constant here. Where was it? Resolution. Number of rows and columns. So we had 100 rows and 100 columns. That was a lot. And that was about 10,000 vertices on the sphere. That was a lot. Wow. I don't know where I picked up that number, but that's a lot. So for the surface, we're going to do something similar, except we're again going to vary it from instance to instance, because in some domains you might want it to be super fine. Like for example, if we had the surface, I'll just type it out actually. 1 over x squared plus y squared. You can see that in the middle, around the origin, you would want a lot of precision to see how this is changing, but after that, it's just kind of flat. So if we say projected the surface over here in this region, we wouldn't care how many vertices we had. We would just need to give it a resolution. Which we're going, well actually I kind of screwed up that explanation. We're going to have the resolution stay the same for all instances just so we can render things properly. So that's going to be something in the constructor. So it'll be int x cells and integer z cells. So this is just the number of cells in the x and z plane that we're going to be rendering across. And we will store these as a variable. But this does affect each instance differently, and I believe we can. Yeah, so we can just keep it at this for now. So the bounds, the diffuse, and the specular, and that's all we need for each instance. But this these two parameters will affect each instance differently based on the bounds and based on the domain. So I'm just gonna initialize the values. Okay. So we have our instances and we just pass in bounds. And we can now define our load function. So void load, we're going to take in a shader here. So shader is equal to a shader, and we're going to pass in all three files, one for the vertex, one for the fragment, and then one for the geometry shader. So the vertex shader path will be surface.vert. That's just the extension for, or the file extension, so that the GLSL highlighter can work. Surface dot or actually we're going to be using the same fragment shader as the sphere, so sphere.frag, and then surface.geom for the geometry shader. And then we're going to activate, so shader.activate. And because these parameters, x cells and z cells, define are global, we're going to pass them in as a uniform variable at the very beginning and never touch it again. So we'll say shader.setInt x cells, and then we'll define this in the shader as needed. Okay. And then now we're going to do our VAO. So VAO.generate and VAO.bind. I don't feel like rewriting the VAO and VBO stuff, so I'm just going to copy it from the sphere. Just because you guys get the gist by now. I'll go over it again, and I'll go over the changes, but you guys get the gist of it. So we only need 3 VBOs. So it's going to be a 4D vector for the bounds. So I'll rename this to bounds VBO. So we set glmvec4, and then this is at index 0. Why do I have my keyboard? Index 0, and it jumps 4 floats at a time. And then the diffuse VBO is at index 1, and specular is at index 2. And those jumps stay the same. Alright, and then now, for render, void render, we need to do shader.activate, VAO.bind, and then we're going to say VAO.draw, except this time we need to be a little more careful. So we have instances of the function, and we need to figure out how we want, so we're going to have to use instancing, and I just remember that that function isn't present in this version, so I need to just add it real quick. Because the current vertex memory function for draw arrays doesn't have instance count. And we'll just say this is equal to 1 by default. So to draw, like I said, we're going to be rendering by instances, so that last parameter is going to be 1. However, we have to determine whether or not we're going to render with indices, but we don't have any vertex data, and you may have noticed that I just completely skipped it. So we're just going to say we're going to render points, so GL points, 0, and the number of points, so the first one is 0, and the number of points will just be X cells times Z cells. If we want to render every point in the grid, it's just this number here. And you might be wondering, well, give me 2 seconds. So once we write the geometry shader, this will render properly, and you might be wondering, well, how? We haven't passed in any vertices. We haven't even allocated any memory for an index VBO. That doesn't really matter because we are just instructing the VBO to render, to make a rendering call this amount of times, and that's just how many points are in the grid. So X cells times Z cells, and that's kind of our resolution. So again, every one of these points will be completely generated in the geometry shader. There's no action done by the CPU to generate these points. We're just telling it to render this many points, one at a time, and it will connect them in the geometry shader. We'll render 4 points per point just to do 1 grid square in the geometry shader. And then cleanup. So it'll be shader.cleanup, VAO.cleanup, and then we have to clean up the lists, so bounds.clear, diffuse.clear, and specular.clear. So I'm going to go over again why this works. So let's create our 2 shaders. So it'll be surface.vert, and then we just need the geometry shader. Oops. Surface.geometry. Okay. So for the vertex shader, we're going to start with our version 330 core, and then layout location is equal to 0 in vec4 bounds. That's the first one, and then we have layout location is equal to 1 in vec3 diffuse, and layout location is equal to 2 in vec4 specular. Alright, and then since we're going to be using a geometry shader, we need to pass data into it so it can actually output stuff. So we have out and output structure, vs out. And we're just going to call it vs out lowercase. So we'll have the minimum bound, so vec2 min bound, vec2 max bound, and these will be taken from the bounds. And then we also just want to pass in colors, so vec3 diffuse, vec3 specular, and float shininess. And let's write our main function. We're going to be adding to this, but just for now, let's do this stuff. So we'll say vs out dot min bound is equal to bounds. Sorry, min is equal to min bounds. Sorry, bounds. Bounds.xy, the first two values, and then vs out.max bound is equal to bounds.zw, the last two components. And then the colors, vs out.diffuse is equal to diffuse, vs out.specular is equal to specular.rgb, and then vs out.shininess is equal to specular.a. However, this isn't all we need more than this, because if we just rendered this vertex and how many ever times we tell it to, this isn't telling us where the point is. We have given it where the point can be, but we haven't told it exactly what cell it's going to be in. And I keep talking about cells and grids, and you might be remembering, if you watch the Conway series, well, we're gonna have to kind of index into a table and use modular arithmetic. But Michael, where are we gonna get the index? Well, lucky for you, OpenGL has something called GL vertex ID, which just stores the counter of the current vertex. And we're going to pass that to the geometry shader. So vs out.idx is equal to gl underscore vertex ID. You see it's a constant there. I'm not sure if the geometry shader has access to it. I can try, but we'll just pass it like so. Yeah. Okay. So this is pretty much everything it needs in order to actually get a point. We have an index and we have bounds. However, we don't have how big the cells are, so we can't really do that. But that will come in handy with, or what will come in handy is our uniform variables, x cells and z cells. And we're going to calculate those in the geometry shader. So I'm going to do a little bit of a flow chart of our shaders. So the way OpenGL renders vertices is the CPU, sends layout variables to the vertex shader, so .vert. The vertex shader can then either jump all the way to the dot fragment shader, or it can go to a middle geometry shader. And this is sometimes implicit. We're customly defining a geometry shader. So the actual number or the values that are passed in between are defined based on what we tell it. So for example, or a good place that we tell it, or one of the places that we tell it, is in VAO.draw. So we tell it GL points, and that then it says, okay, we're passing 1 point at a time. or actually geometry shader is something else, but oh, no, it's just max vertices. I screwed that up. Nope, keep screwing it up. So GL points means we pass one point from the vertex shader to either the geometry shader or the fragment shader. And then the geometry shader can pass max vertices every time. If we do GL triangles, then the vertex shader will do 3 points. Or it can be lines where it'll be 2 points. So points is 1. GL lines is 2, and GL triangles is 3. So we're passing in points, so every call to the geometry shader will be getting a singular instance or a singular instance of this structure here. So in the geometry shader, I'm just going to copy this in. We first have to do our version 330 core. And then we're going to take in this structure. So it'll be in, the name has to be the same. So VS out, but we'll call it GS in, and it's going to be an array. This array is just general. So it can be 0, 1, 2, or 3, but we're only going to need the first element because the other ones don't exist. So we have an index, min-bound, max-bound. And then we also need to define to the geometry shader how we're taking in points so it can allocate memory properly. So we take in points, and that's just done through a layout function. So layout, and we just define the type, and that's going to be points. Take it in, and then we output a parallelogram, or output 2 triangles with an adjacent side. So we're taking, essentially, we're taking in the bottom corner. So the shader, the vertex shader passes in the bottom corner, so it passes in X and Z, or enough information to calculate X and Z. And then, so X and Z, and then the geometry shader is going to pass in 4 points to the fragment shader. It'll do XZ, or sorry, it'll be X FOOZ X plus delta X F10Z X F01Z Z plus delta Z, and then X plus delta X F11 and Z plus delta Z. So we're essentially just marking all the corners on the square, and that's just 4 points. So again, we have X FOO Z X plus delta, or that's actually the Z axis. So X F01 Z plus delta Z. And then this corner is X plus delta X F11 Z plus delta Z. And then finally X plus delta X F10 Z. So those are the 4 coordinates. So we're taking points, sorry, misspelled that. And then we're going to say layout, and we're going to output triangle strip, just so it automatically connects the 2 triangles. And then max vertices is equal to 4 out. And this is where that max vertices comes into play. This is well defined. We can't say 1,000, that the geometry shader can't do that. So we can only, again, we can only do 1, 2, or 3 points, and it's not going to define 1,000 points out of it. So that's why we need to essentially render empty data, or just call the vertex shader for each point that we want to render, and then just have the geometry shader calculate everything else. So we take in one of these structures, and then we need to output a bunch of stuff to the fragment shader. And I'm just going to copy all of this, the input to the fragment shader, and paste it, and then replace the in keyword with out, so it sends it to the fragment shader. And we just need to allocate or set values for this. And then we also have our uniform mat4 projection view. And as with the arrows geometry shader, we're going to have a function called send vertex. So void send vertex, which is takes in a position and a normal. So we'd set fragment position is equal to pose, normal is equal to norm, and then GL position, what we actually render, is equal to projection view times the position as a 4D vector, and then we emit a vertex. And this emit vertex calls the fragment shader, or essentially sends stuff to the fragment shader to be rendered. And the fragment shader will run once we send it 4 vertices. All right, then we're going to do our main function. So void main, and since all the points have the same colors, we're going to say diff map is equal to gs in at 0, so the 0th element, the 0th structure, so this dot diffuse. Spec map is equal to gs in at 0 dot specular. Shininess is equal to gs in at 0 dot shininess. And then we're going to want to calculate our points. So we're going to end primitive after everything, but we need to calculate points. We first need to do a couple things. We have our origin point, but we need to determine, we actually don't even have our origin point, so we need to calculate the origin point and then calculate the increment. So we're going to take our index and we'll get a float x and a float z. So it doesn't really matter the order that we do this, but we'll consider x as the rows and z as the columns. So to get the column value, we're going to take the integer division. So x is equal to the float conversion of gs in at 0.idx, so the index, divided by x cells. So we get how many rows we've done so far. And then we have to multiply this by some incremental value to convert it into an x coordinate. So let me go back here. So we essentially have some min x and min z value. These are our bounds. We also have a max x and a max z bounds. And I'll draw a rectangle here. Oh, that was perfect. Almost. And we have a bunch of cells in here. And this, the number of cells is defined by, we have x cells going up and z cells going across. And that's defined globally in the constructor. So we take that into the uniform value, and each one of these little increments here, so z increment, is going to be equal to max z minus min z over z cells. And the same thing for x cells, and that just gives us the increment in world units, or in just scene units, to get to the next point. So we need to take in our uniform values, so uniform int x cells and a uniform int Z cells. Yeah, so we will then use these uniform values to calculate the increments down here. And that'll be, sorry, I'm a little disorganized. Give me 2 seconds. Here we go, okay. So we say float x increment is equal to the end. So we take in, sorry, max bound. So gs in at 0, in at 0 dot max bound. Justin, I could probably beat you up. I mean, if you let me, then it wouldn't be much of a competition. But if you're challenging me, then we can see. We have to do max bound dot x minus min bound dot x, and divide this by the float value of x cells, and then the same thing for z, except this time we're taking the max bound dot y, because it's just the second component. It has nothing to do with x, y, or z. And then we divide it by the float conversion of z cells. So to calculate the point, the origin for our cell, we essentially get the proportion or the number of rows that we've done so far using integer division. And then we multiply this by the increment, so x increment, and then we add the origin, or add the minimum point. So this is going to be gs in at 0 dot min bound dot x. And then for z, well, let me actually just go over this calculation real quick. So we essentially have our index, which goes 0, 1, 2, 3, dot, 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 and let's say 10, 11, 12, 13. So to get the row, we just go index divided by 10, integer division. That gets the row. And then we need to calculate the proportion, or the actual world unit. So we calculate the row by, or multiply the row by x increment, because this just gets the number of world units to get to that row. So x increment, x increment. So if we're in the first row, we need to go 1 x increment up from the minimum x value. And then we need to then add min x, so we can actually go in the proper spot. And then z is the kind of other way. We do the integer value of idx modulo 10, get the column. So we'll say this is equal to the float value of gs in at 0 dot idx modulo z cells this time. So this needs to be, if it's 10, it's, did I actually do this right? Oh. Wait, no, the increment is correct. And then, yes, this should be divided by z cells, sorry. So the index divided by z cells just to get the number of rows we've gone. And then we modulo z cells as well, times z increment this time, plus gs in at 0 dot min bound dot y. And once again, this is just this is not y, it's just the second component. So we now have the origin point of our current square. And we now want to calculate our point and what the normal vector is given this, and we're going to essentially just do it using a helper function. So we'll have a function called calculate and send point. What's my view on OpenGL 4.5 and compute shaders? I have no clue what that means. I'm just sticking with 3.3 because that's what I learned, and I'm not sure if it's any different. I don't know what compute shaders are, but I'll do some research. I can look into that. So we're gonna have a helper function calc and send point, pass in a float x and a float z. So this is essentially the point that we're calculating. Whether or not it's incremented, it doesn't matter. And then we just calculate the normal vector at that point. And what's great about generalized surfaces is that we can have this smoothly defined function that gives us a normal vector for at each point, no matter where we are in the plane. So we will say we're going to calculate first the height, so float y is equal to, and for our function, we can also just have a helper function. This can be what we customize. So float x and float z, and for our purposes, let's say return 1 over the radius or the Cartesian distance to the origin. So x times x plus z times z. And then float y is just going to be the function at that point. So x and z. And then let me actually do something a little clever here. Let's return a vec4 just as a collection of 4 numbers, and we'll call it func and normal, just so we can optimize a few things, because with a function like this, it's easily optimizable. So we say vec4 y norm is equal to func and norm evaluated at x and z, and then we're going to we can actually just get rid of this send vertex function and just put it in here. So send, we'll keep send vertex for later, but for now it'll just be, so for calc and send point, we have fragment position is going to be, the position will be the vec3, and we're given x and z, and then the y value is just we'll return it as the first value in y norm dot x, just as the first component, and then z, and the normal is y norm dot yzw, and then GL position is projection view times the vec4 fragment position. So fragment position here is just where we are in the world, and then we're going to transform that using the projection view matrix that we calculate in the main file. And then func and norm will be customizable. So this is, and let's do our function. So we'll say float y is equal to 1 over x times x plus z times z. So 1 over the Cartesian distance. And let's go through how to calculate the normal value. So we have y is equal to f of x and z is equal to 1 over x squared plus z squared. Now, again, let's just do this as a point. So r of x and z is going to be x 1 over x squared plus z squared and z. This is not defined at the origin. And let's take our partial. So partial z. So the first component is 0, and then the partial derivative of this is going to be minus 2z over x squared plus z squared all squared, and then 1. And then similarly, the partial derivative with respect to x is going to be 1 minus 2x over x squared plus z squared all squared, and 0. Don't worry about how I did that. You can plug it into a calculator if you want to know how. So we take the cross product. Now I'm just going to do this quickly. So we have n is equal to I hat is 2x over x squared plus z squared squared. I hat j hat is plus j hat, and then k hat is 2z over x squared plus z squared squared. Right? Yep. Okay. And so yeah, that's the normal vector. And what we can do now is just plug this into our shader. So float y is this value. And then the normal is going to be it's going to be 2 times x. And then if you just recognize this, this is the denominator is just y squared, or 1 over y squared. So this can just be 2x y squared I hat plus j hat plus 2z times y squared k hat. And again, we don't need to worry about, oh, well, can you just define this for any point in the 3D space? Well, you can, but again, we're calculating the y coordinate, so we're not passing in that. So it's not a valid calculation for all points in the 3D space. So we have the normal is going to be vec3, 2 times x times y, 1, and then 2 times z times y. And then we're going to return the vec4 of y in normal. And that should do it. So this is the function, f of x and z. And this is going to be df dz crossed with df dz, or crossed with df dx, right? Is that what we had? Yeah, that's what we had. Or sorry, this should be r, because not f, because that's a scalar. And we have r of x and z is equal to x, f of x and z, just for the comments. Okay. Let's run this. We actually need to add an instance here. So let's first go back to our main file and then include the actual program. Include program/surface. And then we will say surface, let's say we'll have 5 instances. X cells, well, this is our resolution. Let's do 20 by 20 and we will increase it from there and see what happens. So let's go ahead and generate an instance. So surface.add instance. The start we'll say is just glm vec2 minus 10. And then 10. And then we'll say the material yellow plastic. All right, and then we register the program with our programs list. So programs.pushback a reference to surface, and the for loops should take care of the rest of it. Okay, something didn't go right. I don't know what, but let's put a breakpoint in surface render to see if it's actually getting called. All right, this number of instances is 1, so it's getting called. Oh wait, sorry. This number, so for draw, it should be 0, then x cells times z cells, and then this 1 should be replaced with a number of instances because we need to render it once per instance. Is that all I forgot? Because that doesn't, it would still be rendering it, I believe. What else did I forget? Okay, let's just run this and see if that changed anything. Alright, as I expected, nothing changed. Alright, wonderful. Let's try... The program gets loaded and... Check the vertex shader. vs_out.index, good. Min bound is bounds.xy, max bound is bounds.cw. Diffuse, specular shininess. Oh, I'm an idiot because I don't call. Okay. One last point in the geometry shader, I shall say. We didn't actually render any of the points, so that's what we need to do. In the main function, we have our origin point, and we need to call calc and send point for each of the points. So we have the 4, we need to calculate it for the 4 points. So calc and send point, we have x and z first. Then we have x and z plus z increment, so we're going to the bottom right corner. And then x plus x increment in z, top left corner, and then x plus x increment in z plus z increment, which is the top right corner. Let's build it again. It's already up to date. Now let's run it. Et voila. Something's wrong, but that's a surface. Bam. Yeah, that's a surface. That's pretty cool. There's a weird thing happening, and I know exactly what it is. But you can see that it's kind of giving you the shape of, well, it's rising in the middle. Let's decrease the bounds a little bit to see if that changes anything. So we'll do it, the bounds we'll just say is -2, because this function really isn't that interesting beyond that, because it's just very flat. You can see that it's a bit more, okay, good. What is that? That's the infinity point. That's where the discontinuity is, because if you are at the origin, 1 over x squared plus z squared is just 1 over 0, which is infinity. So this is exactly what we want. The lighting isn't too smooth, but I don't like that at all. We can create a little bit of a bound, but this is our surface. We can go ahead and increase the resolution also. So let's go back to, or let's just do -5 to 5. And we'll increase the resolution to be, let's say, 50 by 50 cells. Okay. And this looks good. We're still getting that thing up there, but I will show you how to fix that right now. But you can see that everything's a lot smoother. So in our geometry shader, what we can do is we can say if y is, we can calculate a denominator. So float denominator is equal to x times x plus z times z. And we can say if denominator is equal to 0, then we just want to give y some absolute value, or some large value. So y is equal to we'll say y is equal to 300.0. And otherwise, we have y is equal to 1 divided by the denominator. And I think this should be a bit smoother. Alright, it's not, no, it didn't make a difference, but we can also just do like if denominator is, if the absolute of the denominator is less than 0.01%. Just give it some value. Oh, what happened? Yeah, and that's a lot smoother. Yeah, that looks a lot better. But yeah, so that's our surface right there. And yeah, so we have the ability to now just generate any surface. I'm going to show you a different surface in a second. Well, I guess I'll just show it to you right now. Let's try doing some trigonometric functions. That'll be a little cool. We will say that float I'll comment this out just so it can be there actually. So ec for func and norm. Pass in float x and float z. Let's say float y is equal to cosine of x plus cosine of z. And we'll return. And the normal vector is just, I'm just going to give it to you guys. It's sine of x, 1 and cosine of x, or sine of z, sorry. And then we just return the vector of y and normal. And we can look at this, and I guess that we can actually, I mean, that's pretty cool, right? You can see how the trigonometry comes into play there. And how the lighting is quite accurate, actually. It's given us a little bit of a pattern. But the normal, that specular stuff is working as it is supposed to, which is wonderful. Yeah, so that's the initial testing. And now let's do instance testing. And what I mean by that is let's try and render multiple surfaces of the same one, because we can have a maximum of 5 surfaces. So let's push back or add an instance. Let's do the bounds this time as vec2 minus 15.0, and then that goes to the corner. So, or you know, let's do minus 5.0 minus 15.0, and then it goes to the corner, or GLM vec2 of 5.0 and minus 5.0 f, and then let's make it red, and we'll see how this works. So we essentially want this should be a second surface along the side. Where are we at? And voila, look at that. That's fucking cool, right? I like that a lot. So this was our initial surface, and it had some value. I don't know what the value was, but it's some value. And it was defined around the origin, but then we have this second surface as a second instance, and we're defining it right off to the left of it, very adjacent to it. So we now have determined that we can kind of piece together different instances, and we could kind of leverage that. Let's say with the other one, well, away from the origin, it's not too precise, just because it's all very flat. So let's go back to the original function, and instead of just going from minus 15 to, well, let's actually look at what this looks like. So you can see that we still have the thing, which looks good, but this is just very flat. Well, let's try and do it where this doesn't only go from minus 15 but minus 100. and it just goes all the way down. But you see that it still has the same number of it still has the same number of vertices, but it's just we don't need that precision because the values are just all the same. And we could also do something like, well, let's add another instance and let's have it go from -5 minus 100, and I want it to go to plus 100 at minus 50. And let's make it, what other materials do we have? What can we play around with? Let's do a jade. I don't know what that looks like. Okay, where are we at? There we go. That's exactly what I wanted. But you can see that the surface, it doesn't matter how far, like, it doesn't matter what the number of, how big the bounds are, because we only need the precision right around the origin. So we could even do something as daring as, like, we could decrease the to 2.5 and have a super precise model around the origin, and then just kind of let everything else dilly-dally around the origin, because we don't care, because it's just all going to be the same value no matter what we do. So that's good. And yeah, even more precise around the origin. And you can see that there's a bit of a curve here, which isn't ideal, but where it's not too well pieced together, there's a little bit of a gap right there, but that's okay. Because who's going to notice that? I mean, I noticed it, but like, that's perfect. That is on the money right there. This is a little less, but that's okay. And I mean, I get that makes sense because with this one, this is a much thinner strip, so it's going to have the same number of Z cells, which is why it lines up perfectly. So you can imagine that the columns are a lot thinner than the rows are in this one. So there are the rows are just much bigger on the jade one, which is very cool. Let's go back to the cosine one and just see, again, just how this isn't going to look good. I'm going to tell you that right now, but we can just try it out. Yeah. So, I mean, it looks cool, but it's perfect. This is like the perfect, the yellow is perfect. The red is meh. It looks good. It'll do this way. Like this way it looks perfect, but then you look at this and it looks like a cone, and you don't want that at all. But here it's just a bunch of misrendered textures that you don't want. All right, so let's take a break from that for now. I'm going to give you an alternative way to calculate the normal vector, because this is there are some functions that, well, I mean, I hate to break it to you, but this little calculation here is not too fun, especially when you have complex surfaces. And if you looked at the normal, or if you watched the normal mapping video, which is somewhere, tangent space, I believe. Yeah, right here, tangent space. What we did was we calculated the normal vectors and the tangent vectors for a complex model that didn't have a well-defined surface. With calculus, it's much easier, but when we have a well-defined surface, we can then use the function. And sorry, I repeated myself. But with calculus, we have that well-defined surface, and that gives us a well-defined normal vector. However, with a model, a custom model like Shrek, what's the normal vector of Shrek? You can't really get something as, it's not as easy as just doing a bunch of partial derivatives. You're going to actually have to calculate it on a vector by vector basis not using a function, you're going to have to use these vectors here. And we're going to, so we'll go back here and we have our, where did I put it? Is it over here? It is here. So we're going to calculate the vector using this little same principle, except we're going to take the actual cross product. We're not going to take any partial derivatives. We're not going to take the limit here because that means calculus. We're going to actually directly calculate the normal vector. Okay. And the way that looks is we're going to have a different helper method this time. It's going to be void calculate points. We have float x, float z, float x increment, and float z increment. So we're going to have vec3 p00 is equal to the function at x and z. So we're just going to calculate it at all 4 points. Sorry. Vec3 should be the function. It's going to be the vec3 of x function of x and z right? Oh, because, yeah, I know why. Because we can't use func and norm. So we have to have a scalar function returning a function, or, you know, let's just return a vec3. Be nice to us. So we take in x and z, and then we just return the 3D point representing the function. So return the vec3 of x, and the function we'll say is the cosine function. So cosine x and cosine of z. Is that okay? Oh, cosine x plus cosine z. All right, p00, and then we have vec3 p01 is the function of x and z plus z increment. And then vec3 p10 is equal to function of x plus x increment and z. And then vec3 p11 is equal to the function of x plus x increment and z plus z increment. So that last corner. And now we're going to send our vertices to the fragment shader. And, you know, let me go back and see how, or let me go back to 1.0. We're going to see how to do this. But it's going to involve send vertex. We're going to do p00 and some normal and some cross product, and then the same for the other ones. Okay, so let's go down, and we have 4 points. You know what? GeoGebra will actually come in handy here. Delete. It's very slow for some reason. I'm probably cranking my Wi-Fi right now. P00, let's say, is equal to 0, 0, 0. P01 is going to be equal to 0, 5, 1. How do I make this a point? Wait a minute. How do I'm sorry, I don't know how to use GeoGebra. There we go. Points. Nope. Zero, 0, 0. Right? And then P01 is equal to the point we'll say 0, 5, 1. What? Okay, I'm gonna go back to 1. All right. Let's say this is P 0, 0, P 0, 1, P 1, 1, and P 1, 0. And with we want our normal vector coming out of the page, so it's coming out like that. So in order to get the normal vector at P 0, 0 coming out, we need to take our two tangent vectors, so along the surface that go to P 1, 0, and then also that go to P 0, 1, and we just take the cross product, and it has to be P 0, 1 minus P 0, 0 cross product with P 1, 0 minus P 0, 0. So the vector here is P 0, 1 minus P 0, 0, and then the other tangent vector is P 1, 0 minus P 0, 0. And that gets us the cross product out of the page. And then I'll just do it for the last corner. But in order to get if you follow the right-hand rule, you need to take the cross product of this vector, so P 1, 0 minus P 1, 1, with P 0, 1 minus P 1, 1. And the cross product here is going to be P 1, 0 minus P 1, 1 cross the other one. And you just have to follow the right-hand rule to figure that out. But we're going to just do that here, so we'll take the cross of P 1, 0 minus P 0, 0, P 0, 1 minus P 0, 0, and then it's just a bunch of the same numbers. So cross. The second one is going to be P 0, 0 minus P 0, 1. This crossed with P 1, 1 minus P 0, 1. Notice how the point that we're calculating for is always always the subtrahend, I think it is, or like what we're subtracting from the other point in the cross product. And then we have cross here is going to be P 1, 1 minus P 1, 0, and P 0, 0 minus P 1, 0. And then finally, we have P 0, 1 minus P 1, 1, and then P 1, 0 minus P 1, 1, just like we looked at. Okay. So let's go back to the main file. So again, we're just setting a vertex using the helper function, which is over here, which emits a vertex. And we're just calculating the cross product using the tangent and bitangent vectors on the surface. And these vectors are guaranteed to be along the surface. At least on the approximation of the surface, which is good enough for graphics. Okay, let's do a single surface. And we'll do minus 6 to positive 6. And we'll keep it yellow, and then we'll run this, and we'll see how the normal vectors change. So I mean, actually that's pretty good. Oh, because we're not even using the new function, that's why. You don't. I need to just reset my brain real quick. Calc points pass an x, z, x increment, and z increment. Then let's run this, and we shall see what it looks like. It's all dark. That's not good. I definitely inverted some of the things. Okay. Oh, yeah, I inverted all of them. Okay. That makes much more sense. So you can just take the first term in the cross product and paste it on the other side. You can do a Shift-Alt, and that'll allow you to select multiple rows in Visual Studio and have multiple cursors. There we go. That's exactly what I wanted. This looks really cool, though. And you can see that the light, like the specular light, is changing, although very slowly, and it's kind of very granulated because we're calculating these vertices using a non-smooth function. And we could increase the accuracy by using smaller increments, and let's try and add more points by making it, let's see if I can take my computer 500 by 500. If I drop out, I'm sorry, but that's almost exactly what we had with the initial one, which you can still see the grid there. And honestly, that's kind of cool. Again, it's the only reason that it's more granulated is because we're taking the cross product using delta vectors that are massive. With calculus, you make that delta vector, the change in whatever, so small that that is just such a smooth function. But with graphics, we're approximating, so you can choose what you want. The second method you can use for any model. You just need a function to give you a height or some point, and you just take it. That's kind of, honestly, we kind of just did normal mapping in a nutshell a little bit, or not normal mapping, sorry. We did normal vector calculation, which is not normal mapping. But we just did a crash course on how to calculate the normal vector, but when we have a smoothly defined function, take advantage of the calculus. It makes it so much simpler, and it looks so much better when you have a very accurate one. And yeah, so that's pretty much all I have for you guys today. I hope you enjoyed. And next one we're gonna do some more surface stuff, I believe, or we'll play around with transitions, maybe. That's on the radar. Or we'll do something completely different. I have no clue. But until then, I hope you guys enjoyed yourselves. I hope you learned something. If you have any questions, drop in the comments. But today is the first video in a couple where we haven't had an undiagnosed error, which is wonderful. But yeah, I will see you guys in the next video. Have a good one.